lovely afternoon, and I appreciate each and every one of you spending your time with us this evening. I'm not straying too far from the mic, am I? No? All right, fantastic. If I do, just, I don't know, let me know somehow in whatever way you deem most appropriate. My name is Jeremy Wilson. I have the privilege of being the undergraduate academic advisor for the chemical engineering program. And not for the first time, I'm sure, nor for the last time, welcome Hokies. I have today well, I just told you what I'm doing here, so let's get on into it. One of the questions that I think a lot of people have when they hear about chemical, yes ma'am. I know. Thank you, yes. One of the questions that folks have when they first think about chemical engineering is, what is chemical engineering, right? Come on, you've thought about it, you've wondered. But I'd like to begin with a different question. Where is chemical engineering? And the truth of the matter is that you probably already know the answer to this, right? Where is it? Everywhere, right? But let's be a bit more specific. When we talk about chemical engineering and where it is, where do we see it in our daily lives? You see it, oh, I've got the clicker, right. You see it in the food you eat. You see it in the drinks that you consume on a daily basis. The hands of a chemical engineer were involved in all of this. Where else do you see chemical engineering? You see it in the drugs that you use on a daily basis to take care of yourself, in the vaccines that prevent you from succumbing to deadly diseases. Chemical engineers made these. You see it in batteries, in power sources. You see it in sustainable materials. You see it in the building blocks of our society. You see it in power sources, in renewable energy. There we go. And you see it in data sciences. This is something that is not necessarily super well known outside of the department, but we have an incredible data analytics program using chemical engineering, or rather using data in chemical engineering to solve chemical engineering problems. So where do you see chemical engineering? All around you, in places that you wouldn't necessarily expect. So then let's go back to that first question. What is chemical engineering exactly? Well, I think that it's a really good way to think about it is this. It's making and it's moving molecules, the ones that the world needs to function every day. Whether that's food, whether that's energy, whether that's sundries like toothpaste, right? That's what we do. We make those, we move those. Three major concepts that you learn throughout chemical engineering are scale up. So what does this mean exactly? Think about a chemist, right? A chemist can make almost anything in a lab, right? But they can only make a relatively small amount of it. That's not great for when you need to make lots and lots of, again, toothpaste, right? Somebody's got to make the machines that scale that up to an industrial level. And that's what chemical engineering was born out of historically, is a need to take chemical processes and scale them up. But you also need to move them around. That's why our students study transfer phenomena. Heat transfer, mass transfer, energy transfer. These are building blocks of our profession and of our field. And likewise, how do you design these processes? How do you design these industrial machines, these industrial activities, right? These are the three cornerstones of what we do and what we teach in chemical engineering. So what does the degree look like? Well, if you want to have the full specific information, you can scan this QR code and take a look at the curriculum. That's the 23-24 check sheet. Does everybody know what a check sheet is? Fantastic. If you haven't been exposed to them yet, they're the best thing in the world, at least from my perspective. But the curriculum is general engineering curriculum. Well, you're all in. How's that going, by the way? Fantastic. Happy to hear it. And along with 44 credit hours of chemical engineering, 20 hours of advanced chemistry, and room for minors and specialty tracks. And our minors range from, well, you can probably guess the most common one is chemistry, but range from that to, I was just speaking to a student today who's minoring in politics, philosophy, and economics, so everything in between. One of the capstones, the things that we are the most proud of as a department is what we call the Unit Operations Lab, UO Lab. This is a class that you take in the summer between your junior and senior year that gives 5 hours of credit that allows you the hands-on experience of being a chemical engineer here in Blacksburg, right? By operating these industrial level experiments in everything from distillation to solubility levels to mass and energy transfer, right? This is one of our most proud achievements as a department and something that we consider an enormous accomplishment for you as chemical engineers to be a part of. But you don't have to take it in Blacksburg. We actually have opportunities for you to take it in Copenhagen, Denmark, as well as in Bochum, Germany. So you have opportunities not only to study here in Blacksburg, but also across the world in Europe. So you may be asking, all this is well and good, Jeremy. Cool, neat. But what else does chemical engineering offer me? How do I use chemical engineering to develop myself? How do I develop job skills? And how do I become a professional worth hiring? Well, my friends, we have answers. First, chemical engineering offers 3 distinct tracks for you to choose to specialize in, areas where you can take additional classes in order to write on your resume or your CV. I graduated with a chemical engineering degree specializing in climate and energy solutions, so things like carbon capture, data analytics, looking at alternative fuels, looking at pharmaceuticals, or health and medicine, looking at things like vaccine production. These are specialized tracks that any of our students can do, not required for graduation, but highly encouraged. We have design teams, 2 big ones off the top of my head. The Chemi car, you can see on the left, this is a car that's powered by a chemical reaction. Last year, we placed, I think it was 2nd in the nation in our competition with Chemi car, using a battery that was built on vitamin C reactions. So, very cool stuff. We also have the Chemi Cube team. Take a reaction, whatever you were told to do for a specific event, compress it into a 1 foot by 1 foot by 1 foot cube. That's the prompt. You can understand that there's a lot of creativity and a lot of work that goes into that sort of design competition. There we go. One of our flagship and largest organizations, the largest organization for chemical engineering, is the American Institute of Chemical Engineers, the AICHE. The AICHE boasts about 250 members across chemical engineering, almost everybody, and it is an organization dedicated to mentorship, dedicated to peer excellence, dedicated to job hunting, dedicated to having an active social life as a chemical engineer. And that's one of the wonderful things about our program. We're a medium-sized program, so you'll get to know everybody, right? You'll be in the classes with the same 80 people throughout your entire time as a chemical engineer. We also have the Omega Chi Epsilon Engineering Honors Fraternity. We lead the university in co-op placements. The entire university, chemical engineering, has the largest percentage of students involved in co-ops, as well as internships. Our students worked with these companies, just to name a few. Your opportunities as a chemical engineer to work with companies to gain real-world experience, to gain opportunities potentially for jobs while you are still a student, is enormous. You also have the opportunity to work with world-class faculty who are involved in research from polymer sciences to biomaterials to sustainable materials. Everything you can think of, our faculty are involved in. And of course, we highly encourage our students to get involved in research, working with these faculty very closely in their world-class laboratories. Oh, just as a specific example, that doorknob you see at the top left, that is a coating that kills COVID, invented by one of our professors. That was the Ducker Lab? Ducker Lab. So, we asked the what we asked the where, so let's get to the why. Why should you study chemical engineering? Good question. I have 3 answers for you. The first is that you're able to change the world as a chemical engineer. And I don't mean that in a trite way, I mean that in a very genuine way. Chemical engineers are responsible for an enormous amount of innovation. They're responsible for an enormous amount of creativity, and they're going to be responsible for changes that happen in our world through technology and through science. And you can do it in a way that makes sense to and is valuable to you. Chemical engineering is an extraordinarily diverse field. I hope I've given you a sense of that already, but you can really go into whatever you want as a chemical engineer, and you can make a difference with it. And you can prepare for a meaningful, lifelong career. Chemical engineers are in high demand. We have very high job placement rates, and these are good jobs, ladies and gentlemen. These are very good jobs indeed, and they're jobs that, again, are meaningful, right? And finally, pursue your passion, right? Chemical engineering is something that grabs you like a bug and doesn't let go. It's something that our students care an enormous amount about. It's something our faculty care an enormous amount about. To be a chemical engineer is to pursue that passion. And that brings me to the close of my comments. If you have any questions, feel free to either approach me at any point after the ceremony. You can reach me via email, wilsonjb@vt.edu, or feel free to schedule an appointment with me via Navigate. You can do so using the QR code on the screen. I'd ask that we just leave that up for like a minute and a half. But that's all I've got for you, folks. Thank you for your time, and I will turn it over to Aerospace Engineering.
Hey, has a minute and a half passed? All right. Can you guys hear me okay? Yeah. All right, cool. All right, so my name is Dr. Ella Atkins. I'm the department head of Aerospace and Ocean Engineering. Most of my background and experience is in aerospace engineering, so I'm giving that part of today's presentation. I love this picture. I've only been here since 2022. I've been in the field for a long time, but I really like this combination. This is a pretty unique department across the world in that it combines both aerospace and ocean engineering. So you can see this cutout where we've kind of pasted an airplane and a ship together. You're not going to be building anything like that because it wouldn't work very well. But regardless of whether you choose aerospace or ocean engineering, one of the exciting things about having a combined department is that you learn a little bit of multidisciplinary content. The water has drag, the air has drag, space doesn't have a lot of drag, but it has some really interesting missions going on. All right, I love this diagram also. We have a lot of cartoons. I'm not going to tell you so much about our specific curriculum. I invite you to reach out to our undergrad advisors and also go to our website, but really, what is cooler than flying? That's why I'm in aerospace, and so here is a little bit about that. How does a plane work? Well, you know, maybe there's some air that flows over things called wings. If you've ever flown out of an airport, maybe Roanoke, maybe somewhere far away, you roll down something called a runway for quite a long distance, and then magically you lift off and start flying. And before you know it, you're on the opposite side of the world. Well, in aerospace engineering, we unlock the secrets. No longer will you see magic as the reason that planes fly. You'll see a variety of subjects, many of which involve math and some programming and all of those things. But in the end, when you graduate, or even when you get an internship or work in a lab or in a student team, you will begin to understand why it is that these big chunks of metal and composite material can actually lift hundreds of people off the ground. Well, and if you think that there's some excitement in airplanes, imagine the explosions that you get to do legally with a rocket. Let me pause there. So many sophomores, I ask, why did you become an aerospace engineer? And they said, because I want to blow things up. Well, it turns out that we have real opportunities in research labs for you to do exactly that with supervision and training to be safe, of course. And so a lot of people really like that. And so here, well, this is some witchcraft where if you've ever seen a rocket launch, there is some kind of thing that's igniting some kind of fuel, and it goes really fast as exhaust out the back, and you see it launch, and then it goes somewhere, hopefully into space, as opposed to self-destructing or being destructed before it gets there. So you see this has three different pieces. One of the things we learned in the 1960s as we were preparing to go really far, like to the moon, is that by having multiple stages, multiple engines, and you drop one of them off and you keep going, we didn't have to carry so much structure all the way to where we're going. So the launches are super exciting when we're going really far because we go up part of the way, and then we dump part of the engines, and then we go up farther, we dump more, and then finally we get this little payload that's either going into Earth orbit or going somewhere else. And somewhere else is really remarkable. We don't do the space science, we don't do the planetary science, but we carry all of the instruments there. We carry the communications satellites into orbit. We do a whole bunch of really cool things, both to launch the vehicles and then to take data and to conduct our mission once we're there. Aerospace is really a merging of two terms, aeronautics and astronautics. Aeronautics is about planes that fly in the air. As you go up from the surface of the Earth, you probably learned this in a class here and there, the air density becomes lower. Eventually, you get to a height where the air density is so low that you couldn't breathe without support. And then eventually, you get so few gas molecules that you have almost no atmosphere, in which case you transition from flying in the air to flying in space. Now, in the aeronautics chart, you can see a variety of different things. In the middle, you have a traditional aircraft. On the right-hand side, you have a really high-performance aircraft that can pull as many Gs as a human can withstand. The limitation turns out to not be in what we can do with the airplane. It tends to be in what the human body can do. So people who are fighter pilots in these aircraft wear pressure suits, and sometimes they pass out. And one of the things I work on is autonomy, which is software that recovers safely, for example, when something goes wrong. And when a person passes out, we have software now that keeps flying. The plane doesn't just crash. On the left-hand side, you see a really high altitude situation that's kind of this merge of air and space where the atmosphere is really dense, or not, really not dense. I said that backwards. And so we have things like hypersonic aircraft that go many times the speed of sound. Well, what's cooler than going many times the speed of sound? Well, maybe flying in space for a long time as an astronaut, but they're both in aerospace and they're both super cool. We are only beginning to explore what we can do in space. Right, over the past couple of decades, new companies like SpaceX and Blue Origin and others have really reinvigorated our entire industry. We now can precisely land a rocket back where it took off. We are carrying people at lower cost to the space station and to other destinations in the near future that were not possible decades ago. We have low-altitude satellites like the Starlink constellation that allow us to communicate anywhere in the world at a reasonable cost and with very little delay. A lot of exciting things are going on, and in science, well, we have an increasing number of opportunities at the moon, at Mars, in deep space, and at all altitudes above Earth. Everything that's above the Earth has to be launched. And so that is a huge part of what the aerospace engineer does as well. Well, what do we do? There's the design of vehicles, right? And you guys will get real experience with designing either a space vehicle or an air vehicle throughout your experience, even just in coursework, but you get additional opportunities if you're part of a student team. So the pictures shown here, I think, speak for themselves. Such a diverse set of vehicles operate now. Anything ranging from something like that hexacopter that you see carrying a little square package. And by the way, if you know anything about aerodynamics, that will hurt you, right? Because a cardboard box has so much drag. But anyway, that's a conceptual picture, and so it is what it is. But you can see crewed vehicles, uncrewed vehicles, launch vehicles, etc. Lots of opportunities. All right, well, so here's some more pictures. You know, one of the things that you should do throughout your mission of education here at Virginia Tech, internships and beyond, is dream. Sketch what you think should be flying, and then your professors, your TAs, your friends will first say, well, that looks really cool, and then they will tell you, so here's how you analyze it, and you can decide how many hours you want to spend trying to do that. Here are the subjects that you'll learn. So the last slide showed some of the concept vehicles that you might be designing. Well, you have to learn about aerodynamics. And if you're going way out into space, it's called gas dynamics, where you actually have to think about the individual molecules of the atmosphere that you're encountering. You also have to understand the physics, the dynamics of each vehicle that you want to analyze. And well, a lot of them are pretty unstable, meaning that they would crash if they didn't have sensors and software. So we have to study how to control them in a manner that makes those vehicles fly exactly like we want. Structures are really challenging in aerospace. A lot of things have really high temperatures. Think rocket engines where the explosions are happening. You don't want to explode the structure while you're exploding the fuel. Think re-entry. Everything gets super hot because of all the friction when you're going from a really fast orbit back into the atmosphere. And we want everything to be lightweight. You never want to fly in air or space with a structure that is heavier than it needs to be, because you have to have fuel, energy of some sort, to keep that structure flying in the air or to launch that structure from the Earth into space. There's a lot of propulsion work here in this department. Faculty study different chemicals to create the thrust, and yes, they explode things in their lab carefully. That's called energetic materials. A moment of silence as I worry as a department head about the explosions going wrong. We have also a lot of system design. Ultimately, if you're working for a company that's integrating all of the subsystems of engines, structures, electronics, software into one vehicle, you have to worry about how to put all the pieces together, how to do something like safety certification to make sure that when you're carrying passengers as an aircraft, you're going to remain safe the whole time, and also how to make the design better. We know how to fly, we know how to launch, we know how to orbit, but we're not done. There are a lot of opportunities to make the shapes different, to make the configurations different, to make the materials, the propulsion systems, everything can be better. And you guys are the ones that are going to make that happen. All right, so you're still just getting started. The advising opportunities that you have are that we have 3 different advisors. 2 of them are here. If you don't mind to raise your hands, Emily and Chelsea in the front row. They have walk-in hours, so if you're so excited about this that you want to see them sooner and talk about aerospace rather than later, stop by. They are in 220 Gilbert Street, which is the new Data and Decision Systems building, Suite 3300, and someone will be there Monday, Wednesday, and Thursday at the morning hours. You can schedule appointments, and you can have a choice of either in-person or virtual advising. All right, so as soon as you get into the major, a lot of you are going to want to get your hands dirty, so to speak, meaning that you're going to want to work in a team, you're going to want to work in a lab, whatever opportunities are open to you. Well, so a lot of students choose to take undergraduate research, and you can take it once, you can take it 0 times, or you can take it every semester. That allows you to get class credit for the research that you're doing. Some of you also may prefer, and if the advisor agrees, great, that you get paid. It's a lot more fun, I think, as a young engineer in training to be doing research in a lab than to be working off campus or doing something else that doesn't involve your future career. So don't think that you're too young. If you look through the website and you see some work that is really exciting and it's what you've always wanted to do, reach out to the faculty member by email, and the worst that can happen is they say, hey, you're a freshman, I need you to wait for another year because you don't have enough coursework, and that may happen. But you'll get some guidance, and then you can come back later. A lot of people have kind of a system where the graduate students mentor the undergrads, and so you get a lot more direct face-to-face time with someone who has more experience than you would get from the faculty member who's still going to be your mentor, but who wouldn't be there every day in the lab. Another thing, there's a ton of exciting teams in aerospace engineering. We have a facility called the Advanced Engineering Design Lab, or AEDL, that has several different choices of rockets. So there's things ranging from small payloads that are launched at NASA Wallops on a large rocket every year, to large rockets that the students design and build themselves, including winding the composite structure, putting the fuel in, building the software and the electronics, and then launching it. We actually have a number of teams that both fly and that launch their rockets at the Kentland Experimental Aircraft Station that is only about 20 miles, or 20 minutes, not 20 miles from campus. So that's a pretty unique opportunity. It has a paved runway to fly drones, and you can see that in the bottom right. That looks like an airport, doesn't it? Right, you can see the markings on the runway and you see a hangar. That's actually a drone port that is owned by Virginia Tech, where you can fly outdoors with permission. Don't show up there and fly as freshmen. They'll get really angry with you, either rockets or aircraft. You have to work your way in through a design team like AEDL or through a faculty member that can help you learn how to be safe as you fly. So you can see some pictures here of things happening. Like the upper right is a student-built rocket launching at the experimental aircraft, or actually at the Kentland Farms facility. There's still some growth going on in the AEDL facility. We have a new team called Gobble Rockets this year that you may have heard of them. They've been reaching out, and they're just another team, right? I don't want to say you all should go to them, but look around. If you're interested in being part of one of these teams, now is the time. If you wait too much longer, then you're not going to get that opportunity. There's a lot of student organizations. Now, don't sign up for everything, but if you choose aerospace engineering and you want to do one or two things, if you don't feel like you have time or interest in a student team where you're going to spend a lot of time in a lab-type environment building and testing, you can instead join one of the organizations, such as AIAA, the American Institute of Aeronautics and Astronautics, which is the primary professional society for aerospace engineering. Most of our faculty and many of our students are members of this organization, and there are several conferences a year and a lot of technical activities. I remember many years ago, I took a freshman to the national conference called SciTech, and I felt like I was going to have to introduce him to a lot of people, but that was not the case. If you have the spirit of entrepreneurship, if you are not shy and enjoy meeting people, I assure you they want to meet you. Before that one conference ended, this freshman had met CEOs of at least half a dozen companies, and they remembered him. We also have other organizations. AUVSI, the Association for Unmanned Vehicle Systems International, is focused on getting unmanned or uncrewed aircraft up into the sky legally, safely, and to support the business cases that have emerged. We have a new phrase for what's going on with new vehicles that fly called advanced air mobility. Some of our alums here at Virginia Tech have really been instrumental in starting companies that have designed concept vehicles that are getting a lot of support from venture capital and that really have an opportunity of becoming the next Boeing or equivalent. Well, if you don't like startups and you prefer companies, there's also a lot of company opportunities in the state of Virginia. Aerospace is huge in Virginia. There's headquarters of Boeing, of Raytheon, and several other companies in Virginia, which gives you a ton of opportunities for internships and for other programs that are not as likely to be available should you not be in the state of Virginia studying. Lots of choices once you graduate. You can go into industry. There's a lot of federal government agencies that study aerospace topics, renewable energy, defense. There's a lot of alums, and they are excited to mentor you, no matter what major you choose. But I would claim that we have a lot of aerospace alums that come back every year and are really awesome about helping with resumes and helping give you advice on how to search for internships and jobs. And please, if you choose aerospace, make sure you learn about that. A couple weeks ago, actually it was just last week, we held this Aerospace Defense and Intelligence Career Fair. Aerospace is very closely tied to the National Security Institute, or NSI. You don't have to be in aerospace to affiliate yourself with NSI as perhaps an undergraduate intern, but there are a lot of people who do. Here's some of the examples of organizations that visited us last week for this career fair, and most all of them were interested in hiring aerospace engineering majors. Here's a couple of names to connect with. If you want to send me email, my name is not here, but please feel free to reach out to me also. Happy to talk with you. And if you choose aerospace engineering, chances are good I'll see you next fall in AOE 2074. Thank you.
All right, can you hear me? Yes, all right. So I'm here to talk about the second side of the Aerospace and Ocean Engineering department, the ocean engineering side. But a lot of things that Dr. Atkins just told you actually apply to what I'm saying now, and I will try to explain that and also tell you a couple of things about ocean engineering. So, by the way, my name is Olivier Couty-Delgauchat, so I'm a faculty in AOE, and like many faculty there, we are on both sides. Okay, we are giving courses on the aerospace side, on the ocean side, most of the time, and there are actually a lot of connections between the different things. The disciplines are many times the same, so that's what I want. The main message I want to actually give you today. So anyway, in ocean engineering, what are we doing? So we are designing vehicles that go into the water. Okay, so that means ships, boats, submarine, autonomous vehicles, offshore structure, everything which is in the water, right? That's relevant for ocean engineering. I should take that thing. Oh, that's that. Yeah. So here we have a couple of numbers which are actually interesting to give you an idea of the importance of ocean engineering, right? 90% of what is transported in the world is transported by ships, okay? That tells you that we cannot avoid that, basically. We have to continue to build ships and to design ships. It's a major thing. Another important thing is about renewable energy. Marine renewable energy, it represents now, okay, the number that you see here, right, which is about 2,000 terawatt hours per year. It's actually the potential that we have in the US, okay? If we were using all the energy that we could based on that, right, we could have this energy, which is about half of the total energy that the US is actually generating. It's 4,000 billions, 4,000 terawatt. Anyway, you understand me. So it means that now we're using only a very small quantity of that. We're using actually only 200, okay, instead of these 2,000, okay? So there is a lot of potential here, and typically in the last 20 years, since I've been a faculty, I've seen a lot of research, innovation in this area, and it still goes on, okay? So if you're interested in this area, that's a very exciting thing, which is really ramping up, and that will continue to develop in the future. Another number here is the Navy budget, right? It's 200 billion, so it's a lot. There is a lot of money here as well, like in aerospace. So it means that there is a lot of research, there is a lot of work for you as well, okay? And I will come back to that later. All right, so what are you learning in ocean engineering if you come to the department? Well, a lot of things that actually also apply to aerospace, okay? Because like I was saying, the disciplines like fluid dynamics, material and structure, okay, dynamic and control, these things apply to both types of vehicles, okay? So, and that's also another thing I want to tell you, okay? It's not the end of the world if you're taking that major or another major. I don't know if I'm supposed to say that, but you know, there are connections between these different things, okay? You can do aerospace even if you do mechanical engineering. You can build cars even if you do aerospace engineering, okay? So it's an important choice. I'm not saying the contrary and you should go where you would like to go, but it's not like it's driving you in a certain direction forever, okay? That's something which is important. And so here, the final product, right, is aircraft, rockets, and in this specific case, boats and ships, right? But really what you're learning here, how to do calculations of fluid dynamics, how to deal with dynamics, for example, and apply control, right, to your vehicles, that's the same thing, okay? It doesn't depend on what you're really building. All right? So, and one important thing is that, one nice thing, I think, is that in that department, right, during your senior year, you are actually designing completely something, okay? You are divided in teams, and you are actually sometimes dealing with a project related to a rocket if you're on the space side, or you're building an aircraft, I mean, you're designing an aircraft, or something related to ocean engineering, right? But that takes you the entire year. You're even doing an experiment to help you on that, okay? So that's something which is really cool in the senior year, to be able to actually work in a project. It's a kind of practice for real-world projects, right? And that's a very good opportunity. I have that, which I should use, by the way. Uh-oh. Yeah. Okay, so what you're learning in ocean engineering, well, is everything, I mean, it's mostly focused on ships and boats, right? So everything which is about hull form, stability, right? In the first course that you will have, if you go to ocean engineering, with me actually, the introduction, you will learn about the stability of ships, right? What to do to avoid that the ship capsizes, right? To make it stable, for example. You will learn about hydrodynamics, which, by the way, is not too much different from aerodynamics, right? The water is different from air, but at the end, it's the same tool, the same kind of equation that you're solving. You will learn about structure and materials, which, again, there are some specificities in ocean engineering because you have corrosion, you have a lot of things which are related to water. But in both cases, you're designing an object which has to, to live during a lot of years, has to be resistant, which has some specific requirement in terms of safety, in terms of structure resistance, right? So it's a little bit the same thing. You have to deal with propulsion as well, okay? Vehicle dynamics and oceanography, okay? So a lot of things related to ships and ocean environment. So same thing, right? You have the same advisors that they are great, right? And you can start talking to them and asking questions. They will be happy to answer, to guide you, and to tell you more about the curriculum, the courses that you can take, and so on. You can also contribute to some design teams, okay? So here I'm talking about design teams across the departments, okay? Many of these projects here, they involve mechanical engineering, aerospace and ocean engineering, sometimes ECE as well. I mean, they are really across the departments. And the one which are really related to ocean engineering, here you have the sailboat team, which is, they are designing a sailboat which is supposed to be operated remotely or with just a very little help of people, basically. And then there is a race and things like that. There is also the human-powered submarine, okay? So they build a submarine which is operated just by people without any additional propulsion, basically. And again, it's a race and things like that. So every year, there is new people joining the teams, and it's a very active design project. So, like has been said before, you have also research opportunities, okay? You can join some labs for undergrad research, okay? And you might have the opportunity like that to work on projects which are funded by agency, federal agency, or sometimes industry as well, okay? Depending on what the faculty is working on, basically. And so something also I want to say on that is that, so like has been said, right, you can be paid for that, which is very good. Usually, right, what happens, reasonably, is that if you are a faculty, right, you want to see first what the student is doing, right? So you would probably, you would probably be happy to give something to do to a new student, even a freshman. That makes no difference in my opinion. I mean, in some cases it can be a difference, but honestly, what the grad students are doing in my lab, okay, most of what they are doing can be done with you, okay? I don't see any reason why you wouldn't be able to do that. You will learn on the fly. You would learn about, the physics behind, about the specific thing that you don't know yet, but nothing prevents you from starting something, okay? And so, but I want to see first, of course, if you really want to do something, or if maybe you just want to observe, which is not that good. So I would probably tell you, okay, let's start one semester. Let's see what you can do, right? And if I see you are really interested, you are really doing something, well, the next semester, I will probably pay you for that, okay? So it's a very good way to start and to be involved, and so, it can be a passion, right? Really, doing research can be really interesting. If you want to do a master at the end, okay, there are also options to do to start your master during your senior year, okay? That's called UGG program. You have time to look at that, but I'm telling you, okay, you can really start your master and save 1 year, basically, doing that, okay? So there are a lot of options to help you and to give you some experience of research. All right, so we talked about the career fair just before, same thing, okay? Ocean engineering has also some professional societies, so it's called here SNAME, okay? There is a chapter of SNAME actually here at VT, okay? They are, if you join Ocean engineering, you will be able to participate to that. They are doing a very good job, actually. They are inviting industrial people, people from industry. They are inviting shipbuilders. They are really inviting people here to connect with the industry and to build a network, okay? So I think it's very interesting. They are really very active. Yeah, and so you have also the opportunity, because of all what we said, right, that there are a lot of similarities between the two programs, aerospace and ocean engineering. You have the possibility to actually do 2 majors, right, with only a few extra courses if you want to do that, okay? So that can be a good opportunity. We have students, I don't know how many students, but quite a lot, right, doing that. Like I said, a lot of things that you will learn, right, anyway, you will learn it, even if you're on the aerospace side or the ocean engineering side, okay? Okay, so once you're done with VT, right, you have a lot of options. And in ocean engineering, so you can go to the shipbuilding industry, okay, which represents a natural, way to source of work. You can also work on engineering firms, okay. Some of the students also continue to grad schools. There are also, because a lot of things, okay, are still connected to military applications, okay. You have also some civil applications. You have, all the type of ships which are not military, for example, right? You have also this renewable energy projects, okay, which, like I said at the beginning, continue to develop, okay? And here there are a lot of opportunities, right? There have been many concepts developed, because if you want to get the energy of the winds, of the waves, you have many ways to do that depending on how you're placing your device, right? And if it's rotating, not rotating, there are many ideas. and it will continue, I'm sure. Okay, so there is a lot of research going on and a lot of opportunity there. All right, oil and gas as well is also a potential source of work as well. Remote sensing, okay, which is at the interface between ocean engineering and other things. And like I said at the beginning, right, if you are joining another department, right, I have a student, for example, who is now joining grad school, right, and he's actually in the civil engineering department, but he wants to do coastal engineering, right? So now at grad school, he's actually coming to AOE to do that, but he has an advisor in civil engineering, right? So he's at the interface between the two things, basically. And it works very well. He's just taking courses in both departments in the grad school. All right, and so something which is important, right, is that the students who are taking ocean engineering, they have no issue in finding a job, okay? If they want a job, okay, there is, you were telling me, Emily, what 100% chance that they will basically get close to that, right? They will get a job like they want, right? So that's a very important point for this specific application. There is a need basically for ocean engineers. All right, and if you want more information, right, the advisor can answer your questions. There is the person here who is indicated is Dr. Seidel, is the assistant department head for undergrad studies in AOE, right? So he's also a good point of contact for you for both sides of the department. All right, thank you.